Welcome back. In the last video, I had had this practice problem that didn't have any problem statement. I just drew the problem and told you that the point of the problem was to obtain an expression for CS2 as a function of time. Just as a quick recap, what's going on here is I've got some salt water initially in this mixing tank 1, and mixing tank 1 is being flushed. So we have pure water coming in, and as time goes on, salt is, as I said, being flushed from tank 1, and it's being sent to mixing tank 2, which initially has some pure water in it. But because the inlet is the outlet from tank 1, we know that it's initially going to come up and then come down if I plot CS of 2. So I want to obtain an expression for that. And in the last video, I obtained an expression for the derivative of CS2, but I stopped short of actually integrating it because in order to do this, I must do it with the integrating factor method. And I've said before that I won't expect you to solve these problems analytically. So analytically means using an integrating factor to obtain an exact expression for CS2 as a function of time. Instead, what I'm going to show you how to do is to solve it using the Euler method, which is a numerical technique. So I've already put in some preliminary information. These are just parameters of the problem. And again, in a previous video, I've told you that a good way to double check your solution is to simply plot it. So I'm going to show you exactly how to do that. So choose a couple of values of t. So I usually like to start at 0, and then I like to just increase by 1 each time. So I get a good range of t values. Let's say 27. That seems good. And I can plot CS of tank 1, for instance. And I know what CS of tank 1 is. It's this 2 times exponent of minus 25 over 50 times t. So this is going to be useful for later, but it's 2 times the exponent of minus 25 times, times whatever value of t divided by 500. And if I wanted to practice good Excel practice, instead of 25 and 500, I would use cell references here, absolute cell references. Remember, a $sign will make it an absolute reference, such that if I wanted to redo the problem later, I could just change the value of V's. Like I could do it for 600 liters if I wanted to. And then everything would automatically update. And I could double click that formula by double clicking the lower right-hand corner. And as expected, the concentration of salt in tank 1 is decreasing as a function of time. Let's do some more. So we should start to see, yeah, it'll asymptote to 0. And I can plot this. This would be very informative to see. And I can plot this by going to insert, scatter plot, and then a smooth line. I guess either one of these doesn't really matter. I think there's less jaggedness with the smooth one. All right, so this plot that I've shown here is the concentration of salt in tank 1 as a function of time. Let me drag this all the way up to the top. Okay, I threw some axes labels on there as well because that is also good practice. And basically the essence of Euler's method is instead of a differential equation, I'm going to treat this equation as an algebraic expression. So in other words, what Euler's method says is for small enough changes in time, so that's the other part of Euler's equation, is I have to choose an appropriate time step. So for a delta t, let's see, what I've chosen here is a time step of 1. So like every time value I'm increasing by 1 second. And because it looks like it takes about 100 to 120 seconds, I think a time step of 1 is going to be somewhat appropriate. Right, I don't want to pick a time step that's too large. I also probably don't want to pick a time step that's too small. I think a time step of 1 is going to be okay. But actually, no, I want to pick a smaller time step, and I'm going to do that specifically so that I show you how you would do it for a smaller time step. So I'm going to change this to be 0.1. And that is, of course, going to change my plot a little bit. So I'm going to need some more values here. So I'm going to need to keep going. With numerical techniques like this, again, it's useful to do this in Microsoft Excel because it doesn't really cost you much, just your time in dragging this all the way down. Let's keep going. All right, and it's very quick to do calculations because all I have to do is drag it. And then just to double check, remember if I click any of these, anything that is referencing an absolute cell reference should still be the same, but the relative cell reference should always be the cell to the left. All right, so I'm going to now change this, and I can do it by clicking on the data series. And I'm going to zoom out and drag these all the way down such that I plot everything that I have. We'll even go past it. That doesn't, you can still go past, and it's not going to plot empty data. Okay. Still just checking that it still looks good, and it still does look good. So my time step is going to be 0.1. And as I said, what Euler's method does is that it decomposes this into an algebraic expression. So I can calculate what dCs2 by dt is. If I just treat this as a variable like any other, it is equal to v dot over v. So I have cell references for that. V dot absolute reference divided by v absolute reference times this 2 exponent of minus 25 over 500 times t is CS1 minus CS2. And see, I need to know what CS2 is. I don't have a value for it. So I'm going to put that value in cell D26. Okay, and this is going to be my CS2 of t. My initial value here is 0, so that's why I'm plugging this in, right? So I know that my minus D26 is now referencing CS2. Okay, now I can calculate the next CS2 by knowing what my change of CS2 is with respect to time. So it is going to be equal to my derivative times my time step. Okay, and I can copy this formula all the way down. Of course, it's going to give me zeros because I don't quite yet know what dCs2 by dt is. I can copy this formula all the way down. Interesting. Now, if I click on any one of these formulas and just double check it, just to check again what it's saying, the derivative is always going to be equal to this expression, and CS2 of t is going to be changing. So let me plot this now. Let me select the data. I want to add all this data so that my x values are going to be my times. I'm going to put it right over the same plot. And my y values are going to be CS2 of t. And I should see that it goes up initially and then down going to 0. I already see that it goes to 0, so that's good. I don't think it should get quite up to 2 grams per liter though. The maximum value should be less than that. And I can't, maybe I made a mistake. I did make a mistake. I forgot to add it to the value before. So my CS, I'm going to start with CS2 for my first time step. It's not simply equal to the derivative times the time step. It's equal to the derivative times the time step plus the previous value. So I need to reference the cell above in each one of these formulas. Now that's looking much better. So let me try and reformat the axis to 2. There we go. So this is what the concentration of salt in tank 2 is going to look like. As the concentration of tank 1 decreases, it's still increasing because it starts off at 0, but then it levels off. So Euler's method you can use to make a plot to show you what the behavior looks like. And just to, again, double check my work and to show you that this is correct, I'm going to input CS2, the analytical expression, which I gave it to you in the previous video. Let me go to my OneNote notebook and get it. Okay, that was my exact analytical expression. So let me just plug this in. So equals t divided by 10 divided by exponent of t divided by 20. Can't just click T, I have to click the cell. There we go. And You'll see that I have pretty close agreement, but not exactly. And that's because Euler's method is not an exact answer, right? It's an approximation. The smaller time step that I choose, the better of answers that I'll have. Had I chosen to do what I originally wanted to do with a time step of 1, let's see what would have happened. Let's say delta t is equal to 1. And good practice of what you should do here is your t's have to have the same time step as your delta t. So instead of plus 0.1 here, I'm going to click plus whatever my delta t is. Right, and let's see, that is going to mess everything up. Oh, because I didn't absolutely reference it. So that would help. Okay, there we go. And now I'm plotting way too much data here. But notice, again, I wanted to point out what the difference is between CS2 of Euler, the Euler method versus the analytical method. Notice how I've got a little bit more error here because I've chosen a larger time step. So the smaller time step I choose, the better my expression is going to be. So the better agreement that I'll have. If I go even lower to 0.001, I've got pretty good agreement now. I'm not plotting enough data here. But as I said, a time step of even 1 would have done it just as well. But 0.1 is a reasonable time step. In general, I like to keep it to about, you want to be aware of what your overall time scale is. So how long does it take for the entire thing to be flushed? It takes about 100 seconds. So I want to choose something that's very small in relation to that overall time. So Euler's method is great because you can do it in Microsoft Excel. It's also great because you don't have to remember how to solve differential equations. You can still plot what behavior you expect to occur. That'll do it for this video. Hope you enjoyed watching, and I hope this is useful to you in the future.